Hey kids, time to start Unit 10. Can you believe we are in our last unit? Unbelievable. Unit 10. So, again, just kind of like with series, those of you that were able to authentically get through the portions of last year as we started remote, there certainly was in your pre-cal class stuff about parameters, parametric equations, vectors, and polars, and we're certainly going to need those now. We will certainly highlight a couple of things, but you're in better shape if you at least had practiced some of that last year. All right, so adding the parameter of time to our normal xy functions. Remember, on the xy plane, we are in 2 dimensions, right? And I can graph anything in 2 dimensions with a function y in terms of x, right? But if I want a third parameter of time in there, I'm still going to graph on the 2D plane, but I'm going to be able to answer the question, at what time did you get to the position of blank blank? So you're going to be given a t interval, and let's say t is, I don't know, I mean, time usually starts at 0, right? But it doesn't have to. But time, let's pretend I'm just going from 0 to 10. On time 0 to 10, what does my normal y equals f of x function do? So I can have points that are x and y on my graph, but at, for instance, time equals 2, what point am I at? I can ask at time equals 10, what point am I at? I can ask things like, at what time is f of x max or min, or concave up or concave down, but I'm asking you at what time those occur. I can ask you about what is y prime at a certain time, right? What's the rate of change at time equals 4, right? So time is now part of our situation. This is often on a calculator portion on the AP exam, so please get your calculator out and stay with me with some of these keystrokes. Hit mode and go down here and choose parametric mode. You are going to want to be comfortable going back and forth between parametric and function mode, because I might want to just look at my function in regular function mode and get points on my regular function to, my y equals x squared, y equals x cubed plus 2, y equals sine of x. But when I want to introduce time into it, I might want to look at my function with time also as part of the calculator's consideration, and then I want to be in parametric mode. All right, so once you've done that, let's practice graphing. So hit parametric mode and then go to your y equals screen. Notice each equation now has 2 components. It has a horizontal component and a vertical component. So the x or horizontal component at any time is just t, right? So when time equals 1, my horizontal component is 1. When time equals 2, my horizontal component is 2. However, my vertical component at t equals 1, my vertical component is also at 1, but at time equals 2, my vertical component is at 4. So 2 equations in parametric mode, horizontal and vertical. So notice if you hit window, you also have a consideration of what time do you want the calculator to graph on. My cursor covered up the negative, and I hope you can see this is just negative 2 pi to 2 pi. If they give you time, like I did when I was saying, oh, what if time was going from 0 to 10? That's what you would put in your T min and T max. T step you usually want to be small, right? You usually want it to be small. If you ever are on your calculator and you hit graph, and you get a graph that looks like this, very right, it means your t-step is too large, right? All right, so this is one equation with two components, horizontal and vertical. And I just set these, I want your x min and max to go from -5 to 5. Don't really care about the x scale. And your y min and your y max also go from -5 to 5, right? For some of the examples. If you haven't already, open up the 10.1 parametric functions note sheet, because the examples and notes that I'm going to do in this PowerPoint go right along with that note sheet. So here's what the graph, if you now hit graph, right? So this is your mode screen, y equals screen, window screen, and then hit graph. And if you hit trace, you now have three things down here. When time equals 1, position is 1, 1. Okay, and how did I get that? Well, I did x1 of 1 and y1 of 1 to get the position at time equals 1. That's just my parabola. If I, and this is a prerequisite skill, right? If you got rid of the parameter, right? If you have x equals t and y equals t squared, right? Get rid of the parameter. T is equal to x, therefore y is equal to x squared. Duh. Okay. Right? That's a parabolic path. But now I can ask about time. Whereas if I just had my function y equals x squared, all I get out of that is position. Right? But now I can say, hey, at 1 second, where is the particle that's traveling this path? The projectile, the whatever. Now check this out. The nice thing about parametric equations, go into y equals and change the parameters, the horizontal and the vertical component, to 2t and 4t squared. Keep your window the same and hit graph. Hey, look, same position, but different time. So, same path, same position, different time. Again, if you were told to get rid of the parameters, excuse me, right? Two squared is 4, 4 divided by 4 is 4. I still get the path y equals x squared. But now time, right, is moving faster. You get to the position 2 times at time. Right? Notice 2 times a half is 1 second. Right? And I get to the same position but at a different time. So that's the power of parametric equations. One of, I should say. Right? There's the first equation. The slope, notice, is the same. Right? If I were to write the equation of the tangent line, and don't forget to write the equation of the tangent line, it's dy dx. You are on the xy plane. XY plane. To write the slope, it's dy dx, not t. That's called foreshadowing. The time that slope occurs, though, this slope occurs, right, at time equals 1, the exact same slope occurs at t equals a half. So it'd be nice if I had a formula for dy dx that I could plug my time into. Because notice, if you have y equals x squared, your derivative is 2x, right? That's awesome. And I can write the equation of my tangent line with that, right? My tangent line would be y equals 2 times x. And my x in both cases was 1. That's the slope times x minus 1 plus 1, right? At the point 1, 1, the slope was 2. That's the equation of this tangent line. That's the equation of this tangent line. But what if I want to know the time at which that slope occurred? Check out when you hit, instead of trace, right? That same menu where you hit trace, look what happens when you hit calculate. There's your trace value, but notice what you have here. Dy dx, that's what you need. That is the slope that you need to write the tangent line. But dy dt is the derivative of the vertical. Dx dt is the derivative of the horizontal. Oh, snap. If you have a calculator in your hand and they ask you for the slope at a point of a parametric curve, do not actually take the derivative. You go here on your calculator and find it. I'm going to give you formulas for finding these derivatives by hand, right, without a calculator, but please know how to access these. If I wanted this slope, if I was in parametric mode, you still have this in, right? This is the one you still have in your calculator. Hit dy dx. Look what it asks for. The time. And you know what you're going to get? 2. But you're not going to get that for dy dt and dx dt. So what are you going to get for dy dt? Well, remember, dy dt is the derivative with respect to t of the vertical. What is the derivative of 4t squared? Hello. What is the derivative of the x component with respect to t? That is the derivative of the x component. What is dy dx? Well, that is a ratio of the derivative of the y component with respect to t. Slope, y is always on top. X compared to the rate of change of dx dt. For t, what is the slope of this equation when t is equal to a half? 2, baby. Oh, snap. I'm going to go through that. I know I'm going through that a little fast. So, regardless of whether I can represent two parametrized equations, which are in terms of points x and y, position, and time, with one equation where you've taken out the parameter, right? Just x and y, that's like y equals x squared. Two parametrized equation would be x is equal to 2t or t, and y is equal to 4t squared. Or our first example where it was just 2t squared. Remember, that was the same equation. I can find dy dx, the rate of change of y with respect to x on the xy plane, the slope of the actual curve on the xy plane. regardless if I have this form or this form. Now, one method is get rid of the parameter, take the derivative with respect to x and be done with it, but you can't plug time into that derivative. So to find the slope dy dx of a parametrized curve where you have two equations is what I just showed you. And this should look familiar. We did this in semester 1. The rate of change of y with respect to x is a ratio of the derivative of y with respect to t and the derivative of x with respect to t, and the t's will cancel out, dt's I should say. Assuming that the denominator is not 0, foreshadowing what if it is? So when I had my example 1, where the x component was t and the y component was t squared, and I'm only using capital T's because I had my calculator. I usually use lowercase italicized t's. Or example 2, where the x component was 2t and the y component was 4t squared, I get the same, right, point. I get the same slope at the time, right? 2t does not equal 4t. These are not the same expressions. They're not equal. However, remember on example 1, oh my gosh, that is a terrible parabola. The point, and here's example 2, was the exact same freaking curve, but at the point 1, 1, I got there at time equals 1. At point 1, 1, I got there at time equals 1/2. So when you put 1 in for time here, you get 2. When you put 1 in for time here, I already showed, I'm sorry, not 1, 1/2, you get 2, right? Because the slope of that line on the dyd, right, on the xy plane is 2, and you can write the equation of that line with the point 1, 1. Now, I keep harping on this because that is a common mistake with students when they're working with parametrics and they're asked to write the equation of the line. They mix it up. They put the time, or, the wrong time, they use the wrong derivative or whatever for the exact same line. So just be careful. So you are plugging in t, the correct t, into the correct slope generator. The correct t into the correct slope generator, depending upon what equations I give you. I'm still on the first page of the note sheet, by the way. So this is the second example. What if I give you two functions in terms of t, right? X is cosine t, y is sine t. If I were to graph that, again, if you were to put this into parametric mode, graph this on the window I gave you, negative 2 pi to 2 pi, you actually get this graph. Oh, I'm sorry. If you just graph the horizontal, if you just graph the vertical by itself, like in regular function mode, on negative 2 pi to 2 pi, you would get this. Ha 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 ha, check that out. But if you graph them in parametric mode, so describing the particle's right-left motion, so your particle at time equals 0, the horizontal component is 1, the vertical component is 0, the motion as, right, you're moving to the right because x is positive, the same time you're moving up because the vertical is positive, what's that going to do to your particle? It's going to pull it in a circular fashion, right? So if you graph these together on the parametrized, you're not going to get the cosine curve or the sine curve. You're going to get the unit circle. Whoa, parametrized. As long as f and g have derivatives at every t, which, hello, love cosine, love sine, of course they have derivatives, Then the parametrized curve also has a derivative that you can plug t into. The derivative of x with respect to t, the derivative of the vertical y with respect to t. Put the two parametrized curves together, as I told you, you're going to get the graph. Oh, this time I did change the t, so it matched my picture there. T is equal to 0. Instead of negative 2 pi, I said 0 to 2 pi. This is just pi over 12. Right, I made it a little smaller than the 0.5 we had. And pi over 12 simply because 12 is the common denominator between all my special unit circle denominators, right? 1, 2, 3, 4, and 6. I shrunk my window, negative 2 to 2. This is negative 2 to positive 2, y min, y max. And there's my circle. My window's a little bit distorted, so it kind of looks elliptical, but it's not. So if I got rid of the parameter, right, which you did in pre-cal, x is equal to sine t, cosine t, y is equal to sine t, square both sides of each equation, add the two equations together, cosine squared plus sine squared is equal to 1, right? Get rid of the parameter, there's your unit circle. But I want to find the slope with respect to be able, I want to find dy dx on the xy plane, but I want to be able to plug time and say at what time do I have that rate of change. Notice that my dy dx has t's in it because I want to say on the xy plane where, at what time do I have this, right, on my unit circle. Plug in a time of, right, I'm going from 0 to pi, so 0 to 6-ish at 4 seconds. What's the rate of change? Where is my point? What's my rate of change? So notice that this is asking where are the points at which the tangent to the curve is horizontal. So if you, right there on the note sheet, first I want to be able to express the derivative in terms of t. I've done that. I could write that as what? Negative cotangent. I choose not to because I'm going to evaluate in cosine and sine. So horizontal tangents occur when your derivative is equal to 0. For my derivative to be equal to 0, I just need my numerator equal to 0. You took Algebra 2 and pre-cal, and you're pretty good at finding out when cosine is 0, right? Cosine is 0 at pi over 2 and 3 pi over 2. And hopefully looking at your circle, that makes sense, right? At t equals pi over 2 and 3 pi over, I can see the horizontal tangents. But that's not the points at which these occur. Remember, the points came from plugging in x was cosine of t and y was sine of t. You need to take these t values and plug them in here to get the position, or psych, you know, this is the unit circle, so this is 0, 1, and this is 0, negative 1. Would you get that plugging in time here? Sine of pi over 2, right, is 1. Cosine of pi over 2 is 0. Sine of 3 pi over 2 is negative 1. Cosine of 3 pi over 2 is negative. But the point is, they asked you for points, you have to go to the position equations, even though you found the time at which those occur. What do you think I'm going to ask you next? Well, you see it on your... I forgot I typed these. Where are the points at which the tangent to the curve is vertical? Your dy dx in terms of t is a fraction. When do you need to be a vertical tangent? Is when your slope is undefined. When is any fraction undefined? Don't forget, don't stop here. You found the time where you had vertical tangents, but you need to take these t's and plug them back into x is equal to cosine t and y is equal to sine t. And of course, on your unit circle, you know where your vertical tangents are, right? And verify that that makes sense. At pi, sine is 0. At pi, cosine is -1. At 2 pi, sine is 0, and at 2 pi, cosine is 1. All right, the second derivative. We did this in unit in the first semester as well. The second derivative of a parametrized curve is the derivative with respect to x of y prime. But remember, y prime, right, with respect to t, the derivative of y prime using parametrized is the derivative of y prime and the derivative of x. Where did that come from? Because I'm introducing t's, right? dy prime dx is the derivative of y prime with respect to t and the derivative of x with respect to t. Don't forget this. Kids often forget that this is down here, and it just comes from the definition of a slope in parametrics. So your steps are, you got to find the first derivative, duh. Then you're going to find this is really the second derivative of y, right? The derivative of y prime, but with respect to t. But then you're going to have to remember to divide by dx dt. This is the step kids often forget. So here was the derivative of y prime with respect to t. The derivative of y prime was a ratio, negative cosine t to sine t. Right? I just replaced y prime with y prime. Then I need to divide, put it on top of dx dt. So I did the quotient rule here. I took this denominator that was here and put it here because that's often what people forget. And I did the quotient rule with the numerator, right? Ho d high. High d ho minus ho d high. Derivative of the bottom. I'm sorry, the bottom times the derivative of the top minus the top times the derivative of the bottom. All over the bottom squared. Hey, that's negative sine t squared. That's negative cosine squared t. Factor out the negative. Combine with this negative makes a positive. And what do you have? A 1 in that numerator. Then you have sine t squared, but that's times negative sine t. Oh, snap. Negative cosecant cubed. Or negative 1 over sine cubed. No, you don't have to write it as cosecant. Sweet. Now, you could have avoided the quotient rule by just realizing that, right, this is negative cotangent and remembering what the derivative from negative cotangent was, right? Negative cosecant. The reason I did it with the quotient rule is because most often you are going to be doing the quotient rule when you take the second derivative. Okay, so I wanted to just model it to remember, for you to remember it. But I could have avoided it. I would have certainly got the same answer. All right, now we're finally on to the second page of your note sheet. So we're going to be using this example for the rest, giving you new curves, right? I worked with very simple ones for the first couple, right? X was equal to t, y was equal to t squared. X was equal to cosine, y was equal to sine. So now I have a little bit more complicated one. Here is the horizontal with respect to t, the vertical with respect to t, and here's the t I'm giving you. You have a calculator, so pause the video and get this stuff into your calculator. So you're putting this in x1, you're putting this in y1, and you are manipulating your window. Look at it. No one is on the AP exam. Are you going to have to sketch this by hand? But look at this. If they ask you to indicate direction, there is going to be a rubric point for it, and refer to your time and your calculator graph. So these are all the questions. I'm going to do them one by one. But I just wanted to, whenever I'm given a problem, I scan it and see what I'm supposed to do. I need to find the derivative dy dx, no t's, right? I make sure that I have a dy dx, so I have to have my formula. Write the equation of the tangent line at a specific time. So I say to myself, I need the derivative dy dx at a point. Identify the rightmost point and justify using my derivatives. Rightmost is a max of the horizontal. How far right are you is your horizontal component, maximum of it. Justify using derivatives is a derivative test. Next, find the points where there are horizontal and vertical tangents. Points, x and y, where the slope dy dx is equal to 0 and the slope dy dx is undefined. Find the second derivative. Second derivative. Think to myself, probably going to have to use the quotient rule. And don't forget, for what values of t is the graph concave up? That's when the second derivative is positive. But they only need values of t, and I have my calculator. Find the length of the curve. Length of a curve on the given interval. So the only interval I'm given is this one. And length of a curve. That's coming, don't worry. All right, so let's start. Hopefully you have done this in your calculator. Now notice I went all the way to -2, right? But really, oh, no, honey. No, don't be fooled, right? I did that on purpose. This is the XY plane. I was like, oh, I should be graphing, right? I made my window -1 to 1.5. Yeah, you did, but it's T. This is the graph I got when I made my T window -1 to 1.5. My X's went from -2 to 0.5, and my Y's looked like that. Okay. Now you may have, right, you may have left your X-min on your calculator, your X-min and your X-max, right, might have been different values, but if you look at where T is equal to -1, right? So, oh wait, I forgot to, so I sketched the curve, but I was supposed to indicate direction. So how you do that, there's a rubric point for it. How you do that is after you sketch the graph, hit trace, and then arrow right, and see where the cursor goes. Where does the cursor go? And if you're not sure, plug in 0 for t. I'm sorry, plug in -1 for t. Right? -1 plus 1. Sorry, -1 minus 1 is -2. -1 minus -1 is 0. Here's where you start at -1, and then if you watch your cursor, it goes like this. So that's all they want, is for you to put some arrows on here. To say that as time, because notice time, this is the XY plane, time isn't there. Your arrows are indicating that as time passes, the particle started here at t equals -1. No, you don't have to label that. And then travels this away. I put way too many arrows. So got that rubric point from my calculator and hitting trace and watching where my cursor moved. I forgot that I did A and B on the same graph. I mean, same slide. B, find the first derivative. So dy dx with parametrized equations is equal to dy dt over dx dt. 1 minus 3t squared over 1 minus 2t. Done. In terms of t, there's the first derivative. I needed to do that by hand because it wasn't the derivative at a point, it was the derivative rule. Done. Rubric points, done. So when t is equal to -1, what is the slope of this curve? I hope I get something negative. When t is equal to some other value, whatever t gets me here, I hope I have a slope that is horizontal. Over here, at t equals, I don't know, 1/8 maybe, I hope I get a slope value that is positive. So at any t, what is the rate of change on the xy plane? That's what the rule that this gives me, and I'm now done with B. I did not use my calculator for this. I did this by hand because they asked for the rule. Even though it was calculator, I had my calculator in my hands. Equation of the tangent line at a point. Now, you just did have the rule, so you can do that. You can do this by hand. It wouldn't be, right, terrible. You could do dy dx is equal to 1 minus 3 -1/3 squared over 1 minus 2 times -1/3. But this is the derivative at a point. You can also, you have your calculator. You can hit, right, that calculate button and get dy dx at t equals -1/3. And it will give you, what did I get? It gave me some fraction. I did it by hand and I got 2/5. But they wanted the equation of the tangent line. Slope, x minus the x coordinate plus the y coordinate. 2/5 is going to go in here. Where do I get the x and the y though? The originals. X of and y of. But again, you have your calculator. This time, right? Go to your calculator and hit trace, and it'll give you the point. I got -0.4 and -0.3. Done and done. So at negative 0.4, negative 0.3, that slope should be positive, is it? 'Tis, honey. And here's its equation. So on a calculator active piece of the rubric here, they would expect, right? Did you get 2/5? Right? So there would probably be one rubric point for here and one rubric point for the entire equation. So probably 2 points max for that, since you have your calculator. Don't do too much work when you don't have to. Forgot to put that in. And again, I did some work by hand, and I got these values. All right, D. Identify the rightmost point. Right goes with horizontal. Most goes with max. Point is an X and a Y. Justify using derivative. So even though this is my calculator, I'm going to get some points for setup. So the horizontal component was t minus what? T squared? So what was using derivatives? Now I can see, hello, that's the furthest right I go. So what is dx dt? We already know that. Set the derivative equal to 0. I have the time at which that occurs. Make sure, since you're doing a derivative test, make sure you show this is a linear function with a slope that is negative. I am just thinking of this on the xy plane, slope that is negative. So therefore, the original is positive to negative, which means right to left. Therefore, this is a max. Remember, on AP, a number chart is work. It is not justification. Justification is, right, that dxdt was equal to 0 at 1/2 and changed from positive to negative. That's where I'm going to get rubric points for that. Therefore, the max, or the furthermost right, I'm done, right? I can go on. I did the horizontal, verified that it was a max, did derivative test and justifies. What didn't I check off? You didn't find the point at which that occurs, right? So you need to go to X and put in 1/2. And you need to go to Y and plug in 1/2. And I hope I get a positive X and a positive Y out of that. And I did. Right, so I have the point at time equals 1/2 when my particle is the furthest right. Looks to me like it is also the furthest up at that point too, but they didn't ask me that. They only asked me for the furthest right. Oh my Lanza, did I type all of this up? I did. Oh, no, I only did that part. So good. All right, next. Strategize. Points. Horizontal, vertical, tangents. Points. X, Y, where dy dx equals 0, dy dx is undefined. So dy dx where the numerator is equal to 0, dy dx where the denominator is equal to 0. That's how I get the horizontal tangents. So again, here's my slopes. Made a ratio of, so I'm going to take, for horizontal tangents, I'm going to take the numerator, set it equal to 0. I don't have to show a lot of work here because I have my calculator. Ooh, that's not surprising, right? And then I bet this is one horizontal tangent. Where's the other horizontal tangent, do you think? Ooh, I bet it's about right there. What do you think? Right, just a little bit before the maximum. All right, so what do I need? So I'm done, right? No, you found the time at which those occur. Now you need to find the points. There's your horizontal tangents. And your vertical is going to be, hey, I already know this one, don't I? What did I get out of these other ones? I don't think I wrote them down. Whoops. I trust you. Again, don't do a whole lot of, right? Use your calculator. Right, and find those points. Looks like about -1 something. Again, we already know this one. Find out. All right, over which intervals of t is the function concave up? Strategy, concave up, second derivative positive, but I only need intervals of t. So I can see concave up, at least I can see, appears to me like I'm concave up, like around there. Can't really tell with that second piece, but it looks to be changing concavity right around that turning point, somewhere around there. And then it looks like it's either concave down or linear. I don't really care. They only asked me about concave up. So I need the second derivative and where the second derivative is positive. But I have a calculator. Right? I am going to find this to demonstrate the quotient rule in case you have to do it by hand. Right? So the derivative with respect to t is dy, right? Step 1 is find the derivative of d of y prime with respect to t. Often takes the quotient rule. There's my quotient rule cleaned up a little bit. Step 2, remember, is to divide by dx dt, right? This is the part that everybody always forgets. So this is the quotient rule, the derivative of the numerator, ratio dx dt. That's the definition of a parametrized slope. The derivative of the y part, it just happens to be y prime with respect to t, and the derivative of the x part with respect to t, and the dt's cancel out. And there I go. I can't really do much with that, right? I could factor a 2 out of this, but it doesn't factor and cancel with anything down here, so I'm not about that. However, I freaking had a calculator in my hand. Now, I did need to get this, right? I can't, like, unlike when I'm in, I can't go to the parametrized screen and use Math 8 to graph. So I did have to use my I did have to find this rule, but then I changed. Remember, I was talking about going back and forth? I took this function and pretended pretended these were x's. And I put my calculator back into function mode, and I graphed it with my calculator. Right? I didn't bother simplifying or doing much to it, right? I just did my quotient rule real quick, didn't forget about this. I do understand that the graph does not exist at 1/2, right? But I put this in. What am I looking for? This is the second derivative. Now, I took away those notes, but what are you looking for? You're looking for where the second derivative for concave up, where is the second derivative positive? Rather than doing any algebra on this, I put this back into function mode, put it in, and looked at where it's positive. Don't look at concave up. No, look at positive. The second derivative is positive up to 1/2. How did I get 1/2? Because because it's broken there. So what's my interval? What's my answer? The second derivative is positive. And remember the interval, they only wanted t intervals, right? The interval was, where did my t start? -1, all the way, the second derivative was positive, all the way through t was what? And not equal to 1/2. Go back to the original graph. Isn't that what it looks like? Now they only asked me for t, right? But if I plug those in, from -1, crazy. And at t equals -1, we were at 2, weren't we? All right, length of parametrized curve. What? I hope you're sitting down. This is, right, we used the Pythagorean theorem. We did all those hypotenuses, hypoteni, and, right, the square root of it really was 1 squared plus those dy dx, right, the change in y of the change in x, all squared. This was first semester. This was the length of not a parametrized curve. This was just the length of the curve. Remember, arc length? Well, I guess that wasn't first semester. That was Unit 8. Well, for a parametrized curve, you're still going to have an integral. But there's your integral, your length. Instead of having 1 squared, you have the horizontal rate of change with respect to t plus the vertical rate of change with respect to t, and it's just Pythagoras. Yep, come on in, right? But it is just the length of a curve is Pythagoras. For parametrized, remember you have t, so instead of 1 plus dy dx squared, you have both derivatives, but with respect to t. So you are integrating with respect to t, so what does that say that these values must be? These need to be t values, okay? So watch out for that. So that's how we're going to do the last problem that I gave you. Find the length of the curve for a given t interval. Again, you have a calculator. So I want to find how long is this? Notice what I did is I went to back to parametric mode. What did I put in here, though? I put in the derivatives. Now, this is what you're going to write out. Don't you tell me what you did on the calculator on your test. Then I went back onto my home screen. Second, quit to your home screen. Call this up, right? When you know how you went, you know how when you usually in your you call up, you go to vars, y vars, function, and then you can call up y1. Well, this time go to vars, arrow over to y vars. Don't go to function, arrow down to parametric, and that's where I got this. Notice these are t values, though. Right? Crazy. What you write down, though, is this. Supposing that you've already found this somewhere in your problem before. Remember, this is the end of a problem. You've already written down these expressions before. You can literally write these in here, or you can just write dxdt squared dy, but you do have to put your -1 and your 1.5 here. Please put 3 places past the decimal. Right? You don't have to tell me what you did on your calculator, and you don't actually have to do that integral. Please don't. You have a calculator. Crazy. All right. We will do some more examples of this when we get together. Oh, I forgot I wanted to tell you about the graph of a cycloid, but I think I will leave that for our live session. All right. I will see you then. Bye-bye.